right, welcome everyone. So what we're going to be talking about today is the combined gas law. So what we talked about before was we talked about these three scientists, Boyles, Charles, and then actually two scientists, Gay-Lussac, that came up with different relationships that they found between pressure, volume, and temperature. And so Boyle's law, I have a way of remembering what Boyle ended up figuring out the relationship to, and it was potatoes and vegetables. In other words, P and V, meaning pressure and volume. And what we had said was they were inversely related to one another. In other words, as you increase the pressure on the system, the volume ended up decreasing. And so we saw a couple of demonstrations that went along with that, and the other way around. Charles' law, we said Charlie's Angels is on what? TV. And so that will show you the relationship between temperature and volume. And what we said was, if you increase the temperature, for example, if you have a balloon and the balloon can expand and contract, then you increase the temperature. What ends up happening is that molecules gain energy, kinetic energy. They start to speed up and they hit up against the side. And what happens to the volume of the balloon? It ends up increasing. And so what we say is, when your temperature goes up, your volume goes up. So what's that relationship? Direct. That's direct. So these two were inverse of each other, but these two are actually directly related. And the last one is Gay-Lussac's law. And we said Gay-Lussac lives in a TP. So now we're relating temperature and pressure. And same thing, if you increase the temperature, the question is, what happens to the pressure? Well, same thing, the molecules are increasing in their average kinetic energy, so they're hitting it up against the side of whatever the container is, and so what do you expect to happen to the pressure? It also does what? Increases. So we call that relationship up and up means it's also direct. Okay, so when we look at the equation, what they did was they put all three together. And so Boyle's law is simply P1V1 equals P2V2. And then we've got TP, that's Gay-Lussac's law, and there's Gay-Lussac's law right there. And then we also see Charles' law, the VT, and we also see the VT that's right there. So what they've done is put all three together into one, and they call it the combined gas law. So it says it was too difficult to deal with three separate equations. So instead, scientists at the time decided to merge them into one. All the above equations were combined into one simple equation. Of course, it's called the what? Combined gas law. All right. So there are three simple rules to using it. One thing is your units have to be alike. Okay? So in other words, if you're in kPa for your pressure, then you need to be in kPa on the other one. If one of them's in atmospheres and one of them's in kPa, you need to convert. Or maybe it's in millimeters of mercury, which is the same thing as torr. You need to convert if they're not both the same. Okay? And then the other thing is you have to be in Kelvin. So the units must be alike and you must be in Kelvin for two reasons. What does Celsius do that doesn't work out when we're multiplying and dividing to figure out? It goes to 0, and then the other thing that Celsius does is it also goes into negatives. We don't want to use negatives, and we also don't want to use zeros when we're multiplying and dividing here. So instead, we use the Kelvin scale. And how do you get to Kelvin? If you're in Celsius, how do you get to Kelvin? Add 273. Really easy to remember. What I said was C comes before K in the alphabet. So if you're going 2K, you add 273. If you're going backwards, you just subtract 273. Okay? And then 2. If a variable is not mentioned, if they do not say anything about the volume in the problem, they tell you the temperature is this, the pressure is that, the pressure changes this, what's the new temperature? And they don't even mention volume. Assume it's constant, and you can ignore it. Okay? So either they'll tell you it's constant, so they say the volume's 1 liter, and then the volume stays as 1 liter. Well, that means it's constant. It's going to cancel out anyway, so you can just get rid of it. You can ignore it. And then if a problem indicates STP, do you remember what STP stands for? Standard, good, temp, and pressure. That's what it stands for. Now, standard isn't actually room temperature. That's not standard temperature. You would think it is, but it's not. Guess what standard temperature is? It's freezing, which is 0 degrees Celsius. They use the freezing of water as standard. So it's 0 degrees Celsius, but that's not what we're going to use. We're going to use Kelvin, right? So what would it be in Kelvin? 273. That's equal to 273 Kelvin. So that's your standard temperature. Pressure, do you remember what it is in ATM?
20.
1, perfect. 1.00 is what we'll use for that. What about KPA? 101.3 KPA. And what about millimeters of mercury? 760. And remember, that's the same thing as the torr. Okay? So if they ever give you a problem and they say you're at STP, what 2 variables do you know? Pressure and? Temperature. Awesome. Again, if you're at STP, what 2 variables do you know, everybody? The T stands for temperature and the P stands for pressure. And so what you would do is you would pick the temperature, probably you would use Kelvin, okay? Because if you're using the math, the equation, then you'd want to be in Kelvin. And then you could choose any one of these standard pressures depending on what the other one is maybe. If the other one's given to you in KPAs, then you'd probably want to use the one with KPAs. Or if it's in torr, you'd probably want to use the one that's in torr. Okay. All right, so before we do any problems, I want to make sure that we have a couple of things that we can get down quickly conceptually, all right? For example, I wrote this here, and I have a DID, which DID spells what, everybody? Did. Okay? What do you think D and I stand for?
Density.
Direct and inverse. Direct and inverse. Awesome. This means that pressure and temperature are directly related to one another. In other words, if this goes up, what happens to your temperature? It also goes up. Okay? Or the opposite. If one goes down, the other one goes down. So then what's I? I is inverse. That means if your pressure goes up, your volume goes down, or the other way around. And then volume and temperature are directly related also. So again, if one goes up, the other one also goes up. Okay? So this problem here gives us a whole scenario, but there's a major word that we're going to take a look at. It tells us, gives us all this information, and then it says, please tell qualitatively what variable would change. What does that mean? Qualitatively means you're not using what?
Numbers.
Numbers. No numbers. In other words, we're not calculating, okay? So we're not going to do any calculations here. And so we want to check to see what variable changes. And in this first problem, it says our volume goes up, so let's just write that down. Our volume is increasing. And then it says the temperature is staying constant and the moles are staying constant. Well, moles are going to make a difference because, let's clear this for a second here. If I add particles into here, then that's representing, the number of particles would be representing however many moles. I could figure out how many moles it was. And as I increase the number of moles, what ends up happening to the pressure of this? Well, you can see that as I add more, what happens to this needle here? It's going up. So as I add more and more molecules into here, my pressure ends up increasing. Is it changing my volume though?
No.
No. Now it could, because if you had something like a balloon and you add more air into the balloon, what happens? It expands, okay? And if you add too much air, what ends up happening? It pops, all right? So it could make a difference unless you have like a steel rigid container, that's not going to happen to unless you reach a point where it does, the top does pop off, where your pressure is too high. So when we come back here, they're telling us that moles are constant, meaning we're just going to keep our moles the same, we're keeping our temperature the same. What's the only other variable that they're not telling us about? Pressure. So the question is, what's happening to pressure? If our volume goes up, then what happens to the pressure? Well, how are they related to each other? Inverse. That means if one goes up, the other one goes down. Perfect. So the answer is that your pressure would decrease. Okay? So let's try the next one. The next one says our temperature decreases. So now our temperature is going down. Our pressure and our moles are being held constant. So we're not changing the pressure, we're not changing the moles. What's the only thing we're not talking about here? We haven't spoken about volume yet. So now it's asking us to relate volume and temperature. Well, how are these two related to each other? Direct. So if your temperature goes down, then you would expect your volume to also go down. Perfect. So then your volume decreases. Let's try the next one. Your pressure goes down, so P is decreasing. Your volume and your moles are constant, so what do we not know? Temperature. So if your pressure went down, how are pressure and temperature related? Direct. So that also would go down. Perfect. And the last one. The last one says the number of moles of gas decreases. So your N is what they're going to call moles. Okay, we'll talk about this when we do the ideal gas law. And they're saying that we're decreasing the number of moles that are inside of the container. Volume and temperature are being held constant. So just like in this picture here, we're going to keep our volume the same. We're going to keep our temperature the same. The only thing we're going to do is we're going to get rid of some of the moles of this. What's the only thing they're not telling us in this problem? Pressure. So the question is, what happens to the pressure if I were able to get rid of some of the moles of this? Decrease. It would actually decrease. Perfect. Okay. So that means that your pressure would decrease in this case. Okay. So if you get moles, think about it for a second. Do you think that moles would affect temperature? If you add more moles, would that change the temperature on a system? Probably not. More than likely, that's not going to change it. Okay. It could change the volume. Again, what does that depend on? The type of what that you have? The material, the container that you have, it depends on the container. Because if you have a container that is more flexible, then it will change. But if it's like a rigid steel cylinder, then that's not going to change. Okay? All right. So now let's try out some problems. First thing I want you to do is let's write the equation, the combined gas law. So I will say it kind of to a tune, okay? You don't have to memorize it. I'll give you all of the values and the equations. But it's P1V1 over T1 equals P2V2 over T2, okay? And you'll see why I say it this way later on, too. Okay, so this is the equation, and now again, for example, let's say our temperature is constant, we get rid of those, and it becomes Boyle's law, potatoes and veggies, okay? If your volume's constant, then you've got a pressure temperature, or TP, which that is whose law? TP? Gay-Lussac's. Awesome. So if one of them's constant, you can just cross that one off, and then you have the other variables left. So this question says, we're going to do this the same way as we've done all the problems in the past. We're going to try to write down what the variable is representing, and then we'll fill in our equation. Okay, circle what you don't know. We're going to keep it the same way. So the gas left in a used aerosol can is at a pressure of 103 kPa. So what is this 103 kPa? Pressure. Now, you'll see later in the problem that they're going to give us or ask us for another pressure. So what we're going to do is we're going to end up calling this our P1. So this is going to be our original pressure, so we're going to call that the P1. And it's at 25 degrees Celsius. What's wrong with that? We need to switch it to Kelvin. How do we do that? Add 273. Awesome. So we're going to get 298 Kelvin for this one. All right, so that's representing T, and we're going to call it T1 because that's our original temperature. You take the can, don't do this at home, you throw the can into the fire, exclamation point, and the question is, what is the pressure? So what are we looking for? P2, circle it. Circle the one that you're looking for. When the temperature reaches 928 Celsius, again, that's in Celsius, so we need to add what? 273. So we get 1112.01 Kelvin. Okay, so now we know our temperature, and this is our T2 then. That's what we're going to call our T2. And now we can fill in everything that we know here. What are they not telling us anything about? Volume. So guess what we can do? Just ignore it. Okay, we're leaving out volume. We're not doing anything with volume. Okay, so let's fill this in. So we've got P1, we know is what value? 103 kPa, good. So that's our P1 right there. And then we're going to divide it by our T1 because we know volume we're leaving out here. So what is our T1 in this case? 298 Kelvin. And now we're going to set it equal to P2, which we don't know P2. So I'm going to write P2 on here. And then we're going to divide it by T2, which we did figure out was 1201 Kelvin. Easy, because now it's just, well, how do you solve for P2? You're going to do what? Cross multiply. So you could write it out, but again, I would rather that you didn't. You're more likely to make a mistake when you have to copy numbers down, okay? So I always say, do your cross multiplication here, but start opposite your unknown variable. Even if your unknown variable was down here, you would still start opposite that. So I'm not going to start on this line, I'm going to start on this line, and I'm going to multiply. So in your calculator, you are going to type 103 times 1201, and then you're going to do what to the one that's attached to P2? Divide. Awesome. Divided by 298, and let's figure out what our units are, and let's find out what our answer is. So 103 times the 1201 divided by the 298, and that gives us 415.1. That's 3 sig figs, 4 sig figs, 3 sig figs. So what would be the answer? 415, and now our units. Okay. When you divide this over to the other side, your kelvins end up, sorry, this one, when you divide this one, your kelvins end up canceling out, and what are you left with?
KPA.
KPA, and that's a unit of pressure, so we're all set. Okay, let's try the next one. So we're going to label it, and then I want to see if you can do this on your own. Okay, so we're just going to label it together, and then you're going to work on this one by yourself, both of these. The volume of a gas-filled balloon is 30 liters. So what's that representing? V1, perfect, that's our original volume. It's at 40 degrees Celsius, so what do we do now? Add 273, and so we're going to get 313 Kelvin, awesome. And now that would represent our T1. And then it says 153 kPa of pressure, so that's representing P1. All right, then it asks what volume in milliliters, so we're probably looking for V2, right? V2, but we want it in milliliters, so just to make sure that we know that, will the balloon have at STP? Are they giving us any other variables?
Yes.
How? STP. What do they give you when they're giving you STP? What is that? Temperature and pressure. What is the temperature at STP? 273 Kelvin. And now we need to know what pressure we're going to use, because we have different pressures that we could use that are standard. We could either use the 1 atm. Again, you don't have to memorize them. These will be given to you. You can use the 1 atm, you can use the 760 millimeters of mercury, or you can use the 101.3 kPa. Which one would you use? Why? Why the 101.3 kPa?
It's already KPA.
Because that one's in kPa. Awesome. So since that one's in kPa, let's use the 101.3 kPa. So again, if they tell you STP, that is giving you some variables. So go ahead and see if you can set up the problem and get your answer on this one. Let's pause. All right, so it looked like most of you were able to get this set up. And so now the question is, can you do the algebra without having to write anything else down? Okay, because I would rather, again, that you didn't write anything else. You're more likely to make a mistake when you do. So if you can just plug it into your calculator, that's your best bet. Once again, we're just going to do what? Cross multiply. So we're going to cross multiply here, which means that one and that one. Same thing. We're not going to start on the line that has our unknown. We're going to start opposite our unknown, and what we're going to do is we're going to multiply. So in our calculator, what we're putting here is 153 times the 30 times the 273, and then guess what you do to the two that are attached to your unknown? You divide, because the idea would be if you cross multiplied these, this all would be to the right of your equal sign. Okay, all of it would be lined up, and you'd want V2 alone. So if these are multiplied by V2, you'd want to divide them to the other side. Okay, so instead of working all of that out, let's just have this pattern down so that we don't have to write anything else. So we're going to divide by the 313, and we're going to divide by the 101.3. So when you do that, the answer that you get will be V2, okay? And what do you get? 39.5? Okay. So here's the thing with this. If we work this out, these were being divided to the other side, and these were being multiplied. So our Kelvin will end up canceling out with the Kelvin there. And our kPa, when this divides to the other side, would end up canceling out with that kPa. And what are you left with?
Liters.
Liters. So this is actually in liters. But what do they want your answer in? Milliliters. If you're going to a smaller unit, remember from a bigger unit to a smaller unit, your number should be getting bigger. Awesome. And because it's liters to milla's 1,000, or it's 3 places, 10 to the third. So all we're going to do is we're going to take our decimal and we're going to go 1, 2, 3 loops to the right. And what does that make our answer? 39,500. And now that's in milliliters. Okay, so that would be your answer that's in milliliters. All right, let's try this one also. So let's label it first, and then we'll label it together, and then let's see if we can get the math going. So 5 liters, guess what that's representing? V1. Then we've got a temperature of -50, but that's Celsius. So what do we do to it? Add 273, which gives us 223 Kelvin. then that's representing our T1. That's our original temperature. Pressure is 107 kPa, so that's going to be our P1. We want to know our final temperature, so we're looking for T2. Circle it. That's what you're looking for. And it says in Celsius. Does that mean that we could just keep that in Celsius? No. You still have to do the algebra in Kelvin, but then you're going to have to switch back out again. Okay? And then they give you the pressure is 126 kPa, so that's your P2. And then this here must be your V2, because that's another volume. All right, let's pause. All right, so once you have this set up, as long as you have this set up correctly, and now it just turns into the algebra. So again, we're going to cross multiply. The ones that are attached to my unknown are these two right here. Even though it's in my denominator, it doesn't matter, okay? You're going to start opposite. So in your calculator, you're going to start by multiplying, and you're going to say 107 is part of this. So we're starting here on the 223. 223 times 126 times the 7. And now you're going to go to the ones that are attached to the T2. Divided by the 107, divided by the 5 liters. And now, when we do 223 times 126 times 7 divided by 107 and divided by 5, we get 367.6 sig figs. That's 3, that's 3, that's 2, that's 3, and that's 2. So how do you round 367 to 2 sig figs?
370.
370. Now, when you multiply and divide, and what is the unit? This is temperature. What unit is this right now?
Kelvin.
Kelvin. They don't want Kelvin. They want Celsius. People said, should we wait to subtract and then do the sig figs? Multiplying and dividing have different rules than adding and subtracting. So do your multiplication division rules and then subtract, okay? That's the proper way to do your sig figs on this one. All right, so then when you subtract 273, so 370 minus the 273, what do you get?
97.
97 degrees Celsius. So we're doing the 370 minus the 273 in order to get that. All right, and that's basically it for working out the combined